Alright, this is example 2 in Module 9, in which we have two parallel wires. They're both long and straight, and they're carrying two different currents, current I1 and I2, and they're separated by a distance d. So the first thing that we're supposed to do is calculate the force that would be exerted on a segment of wire from the top wire. So if we draw a segment of the wire, a length L, we want to know what would the force exerted on that wire be. Now, where is this force coming from? Well, the current in the bottom wire is going to produce a magnetic field, and that magnetic field can then exert a force on currents. So the magnetic field due to the bottom wire is going to exert a force on the current in the top wire. So if we knew what that magnetic field was, right, we knew how to calculate what the force exerted on current is. The magnitude of the force is just ILB sine theta. We're looking at the force exerted on the top wire, so that's going to be I1. The length of the segment we're looking at is lowercase l. The magnetic field is going to come from the bottom wire, so let's call that B2. We need to calculate what that magnetic field strength is going to be. And then this angle, theta, is the angle between the magnetic field due to the bottom wire and the current in the top wire. So let's look at a head-on view. So let me draw a different view that would be from this perspective. So if I look at the wires from the right there, I have the top wire that comes out of the page and the bottom wire that comes out of the page. So this would be I2 and this would be I1. Now the bottom wire is going to create a magnetic field. We determine the direction of this magnetic field using the right-hand rule, where we point our thumb in the direction of the current, so that would be out of the board, and then our fingers curl in the direction of the magnetic field lines. And the magnetic field lines are going to be circular, and in this case they're going to point counterclockwise. So if I look at the magnetic field that is produced by current 2 at current 1, the vector is going to point straight to the left, and it's going to have some magnitude B2. The current comes straight out of the board, so we see that this angle is 90 degrees, which means that sine of that angle is equal to 1. So we can rewrite this force as I1L times B2. Now, because it's a long straight wire, we can use the formula for the magnetic field due to a long straight wire. Recall that that is mu naught I over 2 pi r, where r is the distance from the current. Now this is the magnetic field that's created by current 2. Let me get this. This isn't specific to current 2 yet. So now for current 2, I have mu naught I2 over 2 pi, and then the top wire is a distance d from current 2. So that means that the force that's exerted on the top wire, or a segment of that top wire, is I1 L mu naught I2 over 2 pi d. And I'm just going to rearrange this. I1 I2. There we go. So that's the magnitude of the force. Now we want to know what the direction of this force is. We don't have a coordinate system. I mean, we could easily draw a coordinate system on here to give us something to refer to, but really we can just say whether, you know, the force is going to point up, down, right, left, into the board, out of the board. So to figure out what direction the force is going to point, we're just going to use a couple of the right-hand rules. So I have already used one of the right-hand rule to determine what direction this magnetic field is going to point. So remember the right-hand rule for determining the direction of the force. You take your thumb and you point it in the direction of the current, and then you point your fingers in the direction of the field, and your palm points in the direction of the force on that current. So if I look at current 1 here, that's the current that has a force exerted on it. So I'm going to look at this here. I need to point my thumb out of the board, so I'm going to write thumb out of board. Then I would need to point my fingers to the left. Which would make my palm point down. So that would be the right-hand rule applied to this figure. Let's apply it to the top figure just to make sure that it's consistent. In this case, I would point my thumb to the right. Both of the currents are running to the right. The magnetic field. So I need to determine the direction of the magnetic field in this top figure. Well, if I look at the bottom figure, we are looking at the currents from the right, in this figure, which means that the top figure is drawn from the perspective of somebody looking at it from the left over here. Which means that if I went back to the top figure, I would see the magnetic field along the top wire pointing towards me, so the magnetic field would point out of the board. So my fingers then would point out of the board. So I point my thumb to the right, point my fingers out of the board, and my palm points down. So down is the direction of the force, which means that these wires are going to attract each other. And that's exactly what we see. We see parallel currents running in the same direction have an attractive force. Parallel currents running in opposite directions have a repulsive force.